Okay, so up to this point, we've been able to identify that we have a frequency hopping jammer in our environment, and to be able to identify and quantify actually that frequency hopper was in fact hopping into and causing damage to or jamming the wireless LAN receiver. You recall we were able to zoom in on that portion of the LAN receiver occupied spectrum and see the fact that a dual tone frequency hopper was showing up, was causing the problem. We exported this into the Agilent demodulation software and proved that the constellation, the symbol constellation, actually took a hit when this dual tone frequency hopper showed up. So now the question is how to identify exactly what is this frequency hopper. Does it have a unique fingerprint that we can record and use for future reference should it show up again, so that we can at least be able to identify and say we understand how that's going to behave as time moves on, and therefore possibly how to develop a mitigation strategy, or at least in another environment much more quickly be able to identify it as a particular jammer that we already know how to mitigate and be able to move forward very quickly in preventing it from causing further damage. So one way we can do this, since it's not a standard carrier, we can go ahead and use what's called the carrier search within Spectro-X. And what this does is to identify all modulated and unmodulated carriers that exist in the entire capture file based on a power level threshold that we can set. A power level threshold that is either an absolute power level or a relative power level above a particular noise floor. Now in this case, since we're going to be looking at this frequency hopper, if I take a look at it in a little bit more detail and I look at the color of the occupied bandwidth of the portion that's modulated and compare it to my magnitude scale here, what I should be looking for in terms of being able to zoom in only on this particular type of carrier alone is a power level that is somewhere around minus 35 or so dBm up to somewhere around minus 15, minus 20. So I'm going to go ahead and set my power level to be minus 30 dBm. And accept that in addition to some other parameters. Resolution bandwidth defines the bin size of the FFT, how narrow individual carriers can be and how closely they can be in the frequency domain and be able to resolve them. And I can also choose the time period, the length of the time portion of the file through which the carrier search is being accomplished. Since I want to get as much data on this particular type of carrier as I possibly can, I'm going to go ahead and search over the entire length of the file, and I'm going to let, for at least the first cut, the program choose the resolution bandwidth that it is going to use in the FFT as it presents the data to me. But if I were to do this, I would probably end up with a substantial number of carriers, because if we recall, there were carriers of these power levels of minus 30 dBm all over the place. Anything that's higher in color intensity than this light green is going to show up. So I'm going to show up with all of these carriers. So I need more information than that. And one other piece of information that I can very quickly take a look at is the duration of the modulated portion of this carrier. So again, if I place my markers, this time I'm going to bracket just the modulated portion of the carrier very closely. Then what I see is that the modulated portion of the carrier lasts for somewhere around 93 to 94 milliseconds. So in addition to the carrier search, I can take the very large number of results from just the carrier search and intelligently prune them down based on additional criteria that I can apply to the list. In this case, what I'm going to do is not only show all carriers that show up at minus 30 dBm or higher, but because of the marker, and because it showed me that the modulated portion was 93 microseconds in length, I want the pruning results to exclude everything that is outside a duration of 85 to 110 microseconds. So it's going to only show me those carriers that were above minus 30 dBm in power and within a duration at that power level of 85 to 110 microseconds, which obviously will include the 93 microseconds in length. Similarly, I've got the ability to add in additional criteria, ranges of peak power, the duration of the carrier, the start time of the carrier, the modulated width of the carrier, the pulse repetition interval if it's a pulsed carrier. In this case, I'll go ahead and just use the time duration and power level, apply both of these criteria, and go ahead and run the search. And when I do that, I will see that I end up with, because of the fairly easy, lax, single parameter applied to the carrier search, that I end up with 104 different carriers all meeting my criteria, some of which are the hoppers of interest, but some of them are the other carriers that I'm not concerned about. But if I then look at the result after then applying additional pruning capability, what I find is a very consistent bandwidth, duration, and power level. So I seem to have focused in on this particular carrier with this duration consistently of 84 microseconds that we had measured with the use of the markers. So I can export this data, tabular data, to any sort of program I want. A simple one would be to Excel, and if I were to save that to a file, which I've already done for this example, bring it into Excel and plot it, sure enough, if I plot the frequency of the found carrier against time throughout the file, I get a very distinct hopping pattern, a very distinct fingerprint that I can record graphically and use in the future. This happens to be, when I start to look across libraries of known frequency hopping waveforms, this turns out to be the hopping pattern of a Bluetooth carrier. So in fact, what my jammer is a dual tone frequency shifted Bluetooth set of Bluetooth waveforms that have been incorporated into this particular spectrum. But just as easily, it could have been any sort of frequency hopper that I was very easily and very quickly able to zoom in on and isolate via the carrier search and then the intelligent pruning of those results, and then by plotting carrier frequency versus time that it shows up throughout the duration of the capture file, produce any sort of graphical fingerprint of any frequency hopper that I would want, as a very readily accessible way for an analyst to be able to take these fingerprints, this library of fingerprints that they would accumulate over time, and identify a particular frequency hopper that they may have seen in the past, be able to look at the frequency hopping pattern, understand how it's going to behave as it moves through in time, and be able to apply the appropriate mitigation criteria to prevent it from causing further damage to the desired waveform.